culture, and then people wanted their kids and their kids to not do the job because they think that it is a bad job to do. Although if you go to different countries, people are doing agriculture in a very good way and earning a lot of money also in this state. Okay, so you will find there is a vacancy in agriculture. Nobody wants to do that. There is a vacancy in metallurgy. There is a vacancy in other departments because everyone, if I hit a stone, I will find first an engineer, second a computer science engineer, or an electronics engineer, or an IT engineer. Okay, so who are those, and what will happen to IITians? Because they have a habit of cracking entrance exam. So after doing IIT, most of you will go for IIM. After doing IIM, what will you do? You will take a job and do something, or maybe write a novel and become Chetan Bhagat. Because then you will realize I was not supposed to do this. Okay, so let us assume that these entrance exams are able to select those who are intelligent. Although my definition of intelligence is a little different. But let us assume that that is true. So who is coming to research? Who are the people who are coming to research? Who are doing masters? Who are doing PhDs? Those who are not selected in IITs. Those who are not selected in IIMs. They are doing research. And then you can imagine the quality of research we'll have, the country will have. Okay, so there is a huge vacancy created in these areas, and demand is huge. Salary is huge. But any salary at graduate level is not enough. You will have a demarcation if you have a high salary. If you are in computer science or if you are in, let's say, metallurgy, you will have a clear-cut demarcation at the graduate entry level. But if you have higher education, then that demarcation will not be much, or even not there, or you will have high paid salary in other areas where there is a vacuum. Okay. Anyways, so let us start with the presentation and tell me that what was the first type of material. We are good, humans are good in categorizing things. Okay, so like North Pole, South Pole, and positive, negative charges. In mechanical, we have plane strain, plane stress, which I will not explain what it is, but we are good in. So any curve is a line when you look at a higher scale. Any curve is a line. Okay. So tell me, if you can divide materials in different categories, what would that be? In how many categories can you divide materials? What? Yeah, divide them. Like how many categories you will make, and name those categories. High strength, low strength, hard, soft, good. Anything else? Yeah.
Materials that are shiny, not shiny.
Shiny, not shiny. That's a new thing.
Based on the physical properties.
Yeah. So shiny, not shiny, or you can also divide by the opaque, transparent, translucent, magnetic, non-magnetic, and conductor, non-conductor. Good. So based on different properties you can define. Any other way of defining it? वो तो हार्ड सॉफ्ट डक्टाइल आसपास ही है. What is ductility? What? You are in computer science. Then? Okay. Yeah, that is true. So ductile and brittle, and that is the kind of experiment you will do today. Probably you have done it before. Okay, so you can divide it in different categories. You can have biomaterials, you can have metallic materials, you can have non-metallic materials, and based on optical property like you defined, based on mechanical strength and things like that, you can divide materials. What was the type of material which came in interaction with human first?
Wood.
Yes.
Wood came.
Wood and food. Food is also needed. Wood is also needed. Stones are also needed. Okay, and then you will see that history is divided based on materials. Yeah, Iron Age, Bronze Age, Copper Age, Dinosaur Age. Okay, so these are some of the pictures of the stones which were found in one of the sites of Harappan civilization is in this city. Come again? Which civilization? Indus Valley civilization. Yeah, what do you want to do with that? Are you asking something or are you saying something?
No, in this city, I guess, Indus Valley civilization.
Is it different from Harappan civilization? Okay. So, then what are these pictures?
Sir, extraction and purification.
Furnace, yes. And what is the picture on the left hand side? It's a bucket. It's a bucket where you put clay, some rods and coal. Have you seen this kind of thing? Okay. So, in metallurgy and material science, the meaning of metallurgy, some of you said, is extraction of metals. Okay. So, that is one part of metallurgy. Metallurgy is associated with metals. Okay. And in order to also study other materials, non-metallic materials, materials engineering is also added. Okay. Because including extraction and their processing and then manufacturing of non-metallic materials are completely different. But because you know that history is divided in by these iron and bronze and all those things are metals except stone age, so except stone, but we didn't make machines out of stone except in Flintstone cartoon, but that's a fiction. So these metallic materials we have studied for thousands of years. Okay, we meaning people, not IIT Ropa. So we have studied it for thousands of years, and so people have developed all the theories related to the extraction of metallic materials, their processing, so that we get a lot of properties. So you can have a steel which has a yield strength of 150 megapascal. That is still too high. And you can have a steel which has a yield strength of 1 gigapascal. Okay. So you can have a steel which has a ductility of 2%, and you can have a steel which has a ductility of 30%, 40%. So steel shows a lot of variety because people have studied it too much, and we have explored almost alloying it with all the elements possible. Okay, what is alloying?
Mixing two metals.
Mixing of two metals.
So that they become.
So if I mix sand with iron, will it be an alloy? Why? I mix.
Should be homogeneous.
Yeah, I can make a homogeneous mixture. I can make a homogeneous mixture of iron and sand. Will it be an alloy? Why?
Sir, it should be chemical also.
So alloy is a solid solution. It's a solution. It's a mixing at atomic level. Okay? You have read about solutions in schools, right? No? Solution नहीं पढ़ा? मैं solution ही तो बोल रहा हूँ. Okay. So solution and mixtures are different. So alloy is a solution, it's a solid solution, and making alloy is kind of over. So then people have started making high entropy alloys. What are high entropy alloys?
So
No idea.
alloy very high metals.
Yes.
More metals.
So why do we call them high entropy alloys?
Usually entropy is like associated with randomness and stuff. So if there are more metals, it's like more chaotically distributed.
What is your name?
Umesh.
Why don't you come to metallurgy? Okay, good. That's a good answer. So if you look at the tomb of Boltzmann, have you heard of Boltzmann?
Yes.
Boltzmann law, Boltzmann constant, small k, this is R by N. Yeah, that Boltzmann, if you have you seen the picture of his tomb? No? If you look at his picture of his tomb, on his tomb what is written? This is the tomb I can draw best. Okay? And this is what is written on his tomb. That's the formula which was given by Boltzmann, and nobody believed in it. Then that's the usual story. That should be an Instagram story for all the scientists. Okay, as long as I was alive, nobody believed on me. And he wrote it. See, he asked to write it down on his tomb, and it's a slap on the face of humanity as long as you go to that tomb and visit this person. Okay, so this particular law is about statistical entropy. There is thermal entropy, there is statistical entropy. Thermal entropy is the chaos, disorder, randomness, whatever comes because of the vibration of the atom, because of the increase in amplitude of the vibration of the atom with increase in temperature. Okay? Statistical entropy comes because of the types of sites or variation you can have. So if I have n number of sites, so let us say I have 4 atomic sites and I have one type of atom, A atom. So how many configurations I can have in this situation? So I have 4 atoms, all of them are same, and 4 atomic sites. How many possibilities are there to arrange this? One combination is there, right? But if I add one different atom, and that's not an interstitial atom, so it must be sitting on one of these sites. Okay, then I will have more combinations possible. Okay, and this number of combination is W, and K is his constant, and that will give you the statistical entropy. So for example, I have iron, and if I put cobalt, if I put nickel, and if I put more similar atoms, which will take these sites only, because if I put carbon, they will not sit here. Okay, carbon, boron, nitrogen, these are smaller atoms. Okay, so if they occupy this place, then there will be too much compression from all the sides and people will throw this atom out. Okay, so you don't want a very weak person to take an apartment in your society. That's what atoms do. We are very civilized. So if you put atoms of same size, equivalent size, then they will have a tendency to go to the similar sites, and your number of possibilities will increase in the way you can put them together. So that number will increase, and that's why they are called high entropy alloys. You understand? And we are kind of starting with high entropy alloys, but after also iron alloying is done. So iron has shown a lot of variation, and in this graph what you see is the furnaces which are used for extraction of iron, and there are different furnaces. So blast furnace also has a history of approximately 1000 years or so. Blast furnace is also very old, and people used to make blast furnaces on the hilltops where the air comes naturally. And what is the reaction which takes place? So blast furnace looks like this. Okay, and the reason is that you have to put iron ore and fluxes, so limestone and MgO and CaO and things like that. And to start the reaction, air is needed, not pure oxygen, air is needed, and that air goes in and reacts with the carbon which is there in the coke and forms carbon monoxide. That reaction is exothermic. Okay, so it also increases the temperature and it also reduces. Carbon monoxide acts as a better reducing agent than carbon, and it reduces iron oxide because it's a gas, so it can permeate through the iron ore which you are putting, and then you will have iron and you will have high temperature, so iron will melt. Okay, it will melt, but coke will not melt. Okay, and that's why we put coke, because we need strength, because we are putting solid and at the end we are going to get liquid. So solid cannot remain on liquid, it will collapse, right? So you need something which can hold it, and that strength comes from coke, and that's why you cannot use coal. Okay, coke is a coal which has been heated so that it gets some strength. Okay. So there are different zones which form. Okay, so here you have a cohesive zone, then the iron drips, so this is called dripping zone. There is a zone where no reaction, no dripping happens, that is called dead man's zone. Okay, and then on the upper side you have all those things coming, and you have a turret. Usually you have a turret, so thing like that which rotates, and you put iron oxide and fluxes and all those things. Why do we want to rotate? Because we don't want everything to get accumulated at one place, so we want to rotate it. Okay, so you can also change the angle of it. Okay, so you can do that. So this is, so people used to make it on hilltops, so very long back, and air will go, so they will make it in such a way that the wind direction is such on the mountain that the air will go inside and the reaction will happen, and they will climb stairs and they will put all the things on the top of the mountain, and iron will come out at the bottom, slag will come out, and they will separate, and they will be happy making swords and spears and utensils and other things. Okay, so this is a blast furnace, and nowadays iron is, because coke is very costly. Okay, so you take coal and then you make coke. Coal is already not there because world need more electricity than iron, and we are producing a lot of steel. Okay, so coal is also used in thermal power plants, and whatever we talk about green energy and all those things, most of the energy is coming from thermal power plants. Okay, so we are on daily basis we are burning coal. Okay, so coal is not very available, and whatever coal is available is of not good quality. So if you have a lot of money, you buy coal from Australia, okay, and then you use it and you make a good steel, and that steel is very costly. But steel is not that costly these days. Steel is completely recyclable. Okay, so there is no waste there, but the pollution comes from the gases which comes out of this process. Okay, what happens to the liquid steel which comes out? Goes to a steel making plant, and a steel making plant, what do? Here we did reduction. Okay, reduction of iron oxide. What do we do? And we have a lot of carbon in this iron, a lot of carbon. Okay, because there is coke, and carbon somehow gets dissolved in iron. Okay, there is a carbon deposition reaction which happens, which is the reverse of solution loss reaction. It's the same thing. So carbon monoxide can at high temperature go back and form carbon and oxygen, and that carbon will be deposited in the iron and it will be dissolved. So you will have a lot of carbon in whatever iron is coming out, More than 2% carbon is called cast iron, okay. Less than 2% is steel, and if you can make it 0, that will be pure iron, okay. So we are not producing pure iron here. So now in order to make steel, you need to remove carbon, right, so that it becomes lower than 2% or whatever percent a user needs, and then you need to add different alloying elements, manganese, chromium, based on whatever property you need. For example, if you need oxidation resistance, you need to put chromium in it, because chromium will form oxide. It has a higher tendency to form oxide. It will form a layer on the surface of the steel, and is he sleeping? You need a pillow? Oh, you are watching. Okay, okay. I thought you were sleeping. Okay. So you mix alloying element, and what happens in steel making process is a oxidation process. Okay. So you have done reduction. You take the iron, you put it in a furnace, and then you blow pure oxygen in it, pure oxygen, okay. And that's why these steel industries were donating oxygen in the time of COVID, because they have this. So you put pure oxygen and oxidize different elements which you have in the iron which you don't want, okay. So you want to reduce carbon, you want to reduce silicon, phosphorus, manganese, and all those things, okay. So this furnace is called basic oxygen furnace, also known as LD furnace, because of two cities, Linz and Donawitz in Austria. The same phenomena can happen in electric arc furnace, okay. The mechanism is different. In this case, pure oxygen goes, and that creates a self-sustainable reaction. So there is no heat given to the system, okay. Heating happens by the reaction. In electric arc furnace, there is a lot of electricity given, and an arc is generated, and that gives you a lot of heat, and then the reaction takes place, okay. Nowadays, because I said coke is not that easy to get, so iron is made by making small laddus, pellets of iron oxide, mix it with the flux, a little bit of flux, and then mix it with a little bit of coal, powder coal. You don't need strength there. Make a pellet, put it in a different kind of furnace where you have support inside, okay, and then the reaction goes on in each pellet, and the carbon will come out in the form of gases, and what will remain is reduced iron, okay. So iron oxide has been reduced to iron, and all the coke has gone, so you will have a lot of pores in it, you will have a lot of hole in it. So the product of that is called sponge iron, okay, and the processes are called direct reduced iron, DRI process, okay. Good. So apart from iron, you can also extract zinc using blast furnace, but that's a different blast furnace, okay. The process of extraction of silver and gold, where most of you might be interested in, but that's a pyrometallurgy route, okay. So there you deal with a lot of cyanide to do the reactions and get silver and gold, okay. But even in metallurgy, we don't study much about extraction of non-ferrous alloys, non-ferrous materials, okay. The focus is completely on iron and steel, which should change with time, but it is not changing. Again, why? Because there is a demand for computer science, there is a demand for iron and steel. Nobody is interested in buying titanium or aluminum or any other thing. So aluminum is second. So we have some companies of aluminum. Most of the companies in the world are making steels, okay. So at one point of time, people used to think, is there a material which can replace steel? Now can you answer that question? Is there a material which can replace steel? Don't ask this question to steel industry. Yeah, they take it on themselves. They are very unhappy with this question. But now, so this question was asked maybe 20-25 years ago. So now can you answer this question? Is there a material which can replace steel?
If there was one, then it would have by now. Right?
Yeah, look around. There is. Look around. Plastics. You used to have bucket and mugs and all those things made up of steels in your household. Look in your kitchen, look in your bags. Plastic has replaced it, and that's a new danger which has come. So now people are thinking, can something can replace plastic? Okay, I don't have an answer for that. Okay, good. So extraction is done, and that part is known as extractive metallurgy. Apart from that, we have physical metallurgy also. Don't look at the pictures, that will not give you the glimpse of physical metallurgy. But after making iron and steel, the molten steel is solidified. Okay, so you pour the steel in something, and then so here you have molten steel, and the steel is coming from either LD furnace or electric arc furnace in a bucket. That bucket is very big, so we call it ladle. Okay, and that ladle, so from that ladle you pour liquid steel in this. This is called ton dish. You don't have to remember the names. Okay, these are different buckets of different shapes, and they have a different name. Okay, technological jargons. Then the molten steel is coming here, and this area is open. Okay, so you should be thinking why it doesn't go out, because of viscosity and a little bit of solidification happens here, and this thing is oscillating. Okay, because you don't want it to stick and jam the whole thing. Okay, so molten metal comes here, but here only it has solidified on the surface. A little bit solidification has happened. Temperature is very lower than the melting point. And then these are rollers. Okay, so these rollers are pushing them to move forward, and then there are sprays of water, sometimes air. So you are cooling that, and it comes out in the form of a big slab. Then you cut it here, chop it at certain distance, okay, 2 meters, 3 meters, and you make different slabs. Okay, these slabs are taken by a crane, a sealing crane, and it goes to a different furnace. Okay, so we are doing actually a very weird process in making steel. First reduction, then oxidation, no meaning of that. Okay, then we cool it, and then we again heat it. So we are cooling it, it comes to room temperature. Then we put these slabs in a furnace which are called reheating furnace. I'm just making a box. It's a furnace. The slab will go inside and it will be reheated. Okay. After reheating, there will be two or more rollers, which will decrease the dimension of this. Okay. So 100 millimeter thick plate will become 20 millimeter thick now. Why are we doing that? Because you can deform materials easily at higher temperatures, not at lower temperatures. Okay, and then you coil it, it will become a very big coil, and it will be coiled like a bobbin of thread. So you have a coil of steel, which you might have seen in a lot of trains. If you have spent some time on railway station for whatever reason. Okay, so that's the story of steel we have. And now you can focus on the picture on the left hand side, and can you guess what is that picture? Iron pillar. Where is it? Why is it famous? It has not rusted. Okay, so your question is, Maninder, your question is that you have to tell why it has not rusted. Okay, there have been many theories. you can find it out and report at least 2 of them. It shouldn't be vague. I have explained you enough about how to write a lab report. And you should be writing in 2 pages, so you don't have to write a whole research article on why iron pillar has not rusted. Okay, so significant enough. Good. What is the picture on the right hand side? A bell. Yeah, it's a broken bell of Santa Claus. Christmas is coming. So many years ago, when Santa was coming to metallurgist, there was a reindeer called Rudolph, and his nose used to blow. No, that's a weird story. This bell is called Liberty Bell. Okay, and this bell was ordered by the state of Philadelphia to be used in the church. And when the bell arrived from a very long distance from the manufacturer, then in the first hit on this, it broke and the crack appeared. Okay, so they couldn't send it back because they had to do the celebration. They were all ready for the party, so they were not interested in sending it back and putting a lot of money in sending it back to the manufacturer and then coming back, waiting for it and installing it. So what did they do? They put it in the newspaper, local newspaper, whoever can do it, you will get grand prize. Okay, so 2 people came, Pass and Stowe. Their name is written on this bell. Okay, what did they do? तुम्हारे पास क्या है? फोन है, लैपटॉप नहीं है? तुम ही से पूछो. हाँ क्या? हाँ, दैट आई कैन सी. फोन तो आजकल सबके पास है. लैपटॉप है? घर ही से नहीं लाए हो? हॉस्टल में रखा हुआ है. क्यों हॉस्टल में रखा है? बहुत वेट है उसका. थोड़ा हैवी है. कितना हैवी है? आजकल तो 20 किलो का लैपटॉप नहीं बनाते मेरे ख्याल से. तो कितना का होगा? फ्लाइट में ले जाने लायक होगा? जल्दी में हो गया. कितना जल्दी हो गया? 9 बजे उठे. आपका नाम क्या है? रोल नंबर क्या है? ओके, आपके पास भी नहीं है. सेम कहानी. Yours is very heavy. Like how many kgs?
I mean, it's like more than normal of these days. Like it's an old laptop. It's my dad's old.
Yeah, I'm older than you, so I know a little bit of story of laptops.
Yeah, so like I thought if I can just view on my phone, then why get well.
So what do you think? I didn't think that people can see it on phone. So why did I write an email, put my time in writing an email and ask you to bring your laptops? Why did I do that? Why am I wasting time on people who don't listen? तुमको जब तुम्हारा बॉस बोलेगा लैपटॉप लेके आने को, तुम क्या बोलोगे? यही कहानी सुनाओगे? सुना देना. Okay. So what did they do? You also don't have laptop? आपका नाम क्या है? रोल नंबर क्या है? 1138. You have brought it and you have kept it. Very good.
Actually open, sir. Like watching it on phone is comfortable while sitting down.
Hello? Is it comfortable enough to watch it on laptop? Are you looking for comfort? Then you should be in hostel and sleeping. What's the difference if you see it on phone and see it on laptop? A little bit bigger screen is there. Yeah? Fine. आपके पास है? आपके पास नहीं है? है ही नहीं लैपटॉप? खरीदा नहीं है. ठीक है. और किसने नहीं खरीदा? आपने खरीदा नहीं है? अच्छा स्टोरी है ना? खरीदा नहीं है कि है नहीं कि लाए नहीं? लाए नहीं. नहीं है नहीं तुम्हारे पास है
Sir, due to some update issue, I haven't got it.
what update issue you have
Sir, I don't know. Sir,
what
Sir, I don't know, sir. I have to contact through that particular laptop then.
which lab what are you talking about
Lenovo.
what update you're talking you have a laptop
Yes, sir.
and the software is getting updated
Yes, sir.
right now it is getting updated
Yes, sir.
could you ask any other friend of yours to bring a laptop to take a laptop did you make any effort to do that
No, sir.
no you took it very lightly क्या ही हो जाएगा मेटलर्जी में लैपटॉप का क्या काम है बोला है हम क्यों सुनने वाले हैं ये ना सोचा आपका रोल नंबर क्या है
Sir, 1136.
1136 ठीक you also don't have you forgot that is good आप बताइए अपना रोल नंबर याद है कि वो भी भूल गए 1231 ठीक okay so what did they do these two people pass and stow look at the picture and maybe you can guess
So they joined it with some other method, like soldering between the crack.
shouldering nahi kiya they have opened the crack a little bit so if you have a sharp crack and if you have a blunt crack the difference is the stresses which will appear at a sharp crack will be too high in comparison to a blunt crack okay so if let us say you have a soft material in which you have a very sharp crack and you pull it the first thing which will happen is not that the crack will propagate the first thing will happen is that it will blunt okay in a soft material in a brittle material this blunting will not happen and it will straight propagate okay so blunting happens because of plastic deformation of the material a material can deform plastically and they so we'll not go in how they deform plastically but they consume a lot of energy okay so if you are applying force you are giving mechanical energy to the system and the material will absorb that energy by doing some work on itself and permanently deforming itself and that is called plastic deformation the deformation which recovers comes back is called elastic deformation okay so both of them are happening so at any point of time a little bit will come back rest of it will not okay so whatever plastic deformation happens that absorbs energy consumes energy and if the material is showing more plastic deformation it is consuming more energy meaning it is giving you more resistance for the crack to grow okay so tearing apart a softer material is not that easy tearing apart a very brittle material is very easy because they don't consume energy okay so if the amount of energy available at the tip is more than the amount of resistance a material can offer a crack will grow right apart from giving the resistance you also have to create two new surfaces if a crack has to grow if a piece has to break into two pieces then there will be two new surfaces right so you also need that energy okay so plastic energy plus surface creation energy is needed in order for a crack to grow if you can somehow decrease the stresses at the tip so that it is lower than the amount of resistance which the material is offering a crack cannot grow right and this is what they did they blunted the crack by putting those pins and hammering them a better solution would be to drill a hole just ahead of this crack or exactly at the tip if you can drill a hole then that will also stop the crack don't try it in glass or in brittle material Okay, so that's what they did. And you can, if you are interested, you can read about this story. It's a long story, but that's the essence of it. And then we come to another story. So there was a flight. You can look at the presentation, and this flight is taking off from Hilo Airport, going to Honolulu Airport, and that's what it is doing, off, on and off, going here, going there. Okay, and the two airports are very close to each other, so the flight doesn't go to a very high altitude, it goes to a moderately high altitude because it has to make a landing very shortly. Okay, and so what happens, you know, it's written. So what happened to the flight? Something happened and one air hostess was gone, one casualty happened. None of the passengers or crew or pilot died except one air hostess. Why did she die? And she was 58 years old. Why did she die?
The pressure.
No, she was not wearing seat belts. That's why she died. Because she was serving. Okay? And others did not die. Why? Because they were wearing seat belts. Okay? And the upper part of the flight was taken apart. Look at the picture. This is why I asked you to bring laptops. then तो ये वॉच में ही देख लेते ऐसे. हाँ, फ्लाइट का उड़ा तो है ढक्कन. So the upper part flew away in the mid-air, and this is the real picture of that flight. The pilot decided, somehow realized that something has gone wrong, so he decided to land it in an island which is between Hilo and Honolulu, Kahului Airport, and there this picture was taken. So you can see the happiness, or on some of the suicidal passengers, the sadness of being alive after this thing happened. No, that's a joke. So so this flight was designed for a very high number of flight hours, and it remained in air for 35,000, approximately 35,000 flight hours. Still this happened because the altitude was very low, and whenever a flight takes off, it compresses its cabin to create good air pressure. Okay, because air gets thinner when you go high in altitude. So there is a compression when the flight takes off, and there is a decompression when you land. Okay, so a lot of, in flights, the most damage happens on the wings because of fatigue. Okay, fatigue meaning cyclic loading, oscillations, vibrations, a lot of them, and you may feel it as soon as the flight touches the ground while landing. Okay, but in this case the body broke, because this happened because of the cyclic loading not on wings but on the body, because the cabin is getting pressurized and depressurized. It has remained in air for less number of time, but it has made more number of landing and takeoffs. Okay, because the two airports are very close. So in one day it is making, let's say, 10 takeoff and landing, in comparison to a flight which is flying from New York to Vienna, which will be probably making one takeoff and one landing in a day. Okay, so a lot of cyclic loading, and because it is not going to high altitude and it is in the ocean, you have a lot of salt in the air. So there is a corrosive environment, and both of them combined broke the upper part of the flight. Okay. Another story, McDonnell Douglas, you can read about it. So why this flight was launched, and there was a door which was designed by this flight company. So suppose this is the door, so you have to do something from inside, you have to switch on a switch from inside and then go out and then lock it. The operator did not know, or probably did not understand, he had a language issue, and nobody also could communicate with him, so nobody understood that the door is locked or not. So what happened? the flight goes in air and this door is not locked. It's a cargo door, okay, not the passenger door. It's a cargo door, it is not locked. So what happens? It opens up in mid-air and hits the upper part, okay, and that breaks the upper thing, also damages the electric panel, and then it's a chain reaction. Okay. So this is a picture of another flight which has had the similar accident. How many people died in this case? All of them. Okay. And this is the real picture of the police of France who are looking for the broken fingers or nails or DNA or hair or ID card or some bag or something to identify this person has died. Okay. So moral of the story is, even if you wear seat belts, yeah, so you shouldn't. Take moral from that story. Okay, so last story is about Liberty ship, and the bell was Liberty Bell, if you remember, that broke. So you know where I am coming to. So Liberty ships were made in the time of Second World War, and each ship had a name given to it. So you see, and these are real pictures. So you see the picture of SS John W. Brown on the left hand side, that's the name of the ship. And on the left hand side, right hand side, you see SS George Washington Carver, and that is a picture taken from an article where they talk about the contribution of African Americans in Second World War. So this is the grand launch of SS Patrick Henry, and then this happens, and then that happens. So these Liberty ships are on the port and they broke into two pieces, and the first reaction of any human would be to blame the workers, and that's what people did. They blamed all the amateur welders that you have not done your job properly, and then further investigation showed that they did not took into account or did not understand well in those days that BCC alloys can show a change in energy for breaking with temperature. Okay. So that's what we will be doing. We will be having, have you done Charpy test before? No? So we have a rectangular specimen, it's a rectangular bar specimen with a V notch in it. Okay. So how many questions I have given you? One, right? Or two? One. So you can also take another question, is that why do we have a notch? If you can answer it right now, that will be good. Why do we have a notch in the sample? Yeah, that's a pretty good answer. So you can have a look on this specimen. So the standard, so we follow a standard for this test, and that standard is ASTM E23, and the dimensions of the specimen should be 10 cross 10 cross 55, okay, all in millimeters. There is a V notch, you can have a U notch, you can have a keyhole notch, but most famous is V notch. So V notch is like V, you have a U notch, you have a keyhole notch, like drilling hole. Okay. So V notch people make, and then you put the sample, and then you have a hammer, that's the hammer, that hammer will hit it, you have a notch here, and it will break into two pieces, and the sample will fly. So you have to be careful that it's a steel, it's a flying steel. Okay. So when you go at lower temperature, the flying tendency is more because it's a brittle fracture, so it shatters. Okay. At room temperature, if we do the testing, it will not fly too much, but it will, because it's mild steel, it's not that ductile also. So if you plot, so on the y axis you plot the energy absorbed by the specimen. Okay. So if the sample is not there, the hammer will go to certain height. If the sample is there, it will absorb some energy. So if the hammer could go to this height without sample, with the sample in its way, it will not go to that height, right? So this difference in height will tell you how much energy has been absorbed in breaking that sample. and that is what you will see on the dial. Okay, and you have to, some of you should take the broken pieces of the sample, take it with you, take it and note down the value of energy which you are getting, okay, and keep it together, because when you have 6 broken pieces it will get mixed up. Okay, so you have to note down the temperature of test, the value of energy, and you have to take the sample, take the picture of the fracture surface, put it in the lab report, also write something about the fracture surface. What do you see? What is your observation? This is why people started writing lab reports, because when you do an experiment there are some observations, you have to write that. Cool? Understood? Okay, so we can start the test now.